Okay, thank you. It's a great pleasure to come and visit Kyoto and speak at the university here. I'm going to talk about using the insights and approaches of science. Excuse me, can you turn the light off? Yes, thank you. Using the approaches of science to teach science, and these also apply to most other subjects as well. Before I start, I want to emphasize that you shouldn't pay attention to this talk because I have a Nobel Prize. That isn't what it's based on. It's based on data and research from many different people doing in many different fields. But some of this comes from my own science education research group that I've now had for about 10 years. Now, the vision that I'm going to talk about here is that, guided by this research on learning, we'll achieve a situation in which all students, whether they're going to be scientists or not, will be much better educated in science. And this will lead to many benefits to society, both having a scientifically literate public, which can make wise decisions on the many large challenges facing the world these days, and then also, of course, will help make the economy thrive that's so based on science and technology. But at the same time as doing that, I think we can not only make teaching much more effective, but we can make it more efficient and rewarding for the teachers as well. And so the rest of my talk is really going to be how I see we can achieve this vision. And so what I'm going to cover today is first talk about two types of learning and two different models for teaching as an introduction, and then talk about research on science learning, the components that make up scientific expertise, how we can better measure that expertise, and then what we know about effective teaching and learning. So the first model for science teaching, which is certainly one I used for many years in my teaching, and I think most everyone starts out thinking about teaching this way, is at first I would think hard about and get the subject figured out all very clearly, so that then I could go and tell my students about this physics, and so tell them how to understand it. And then I would give them some problem to solve in the exam, and if they could do it, good, it was successful. If they couldn't do it, well, then it must mean there was something wrong with the students. They were lazy or poorly prepared because I obviously understood the subject. And so if you're mean, you just decide you should get rid of the students and fail them. But I'm not so mean, so what I would usually do is try and tell them again louder and hope that they would understand it. Now, this basic model of figuring out the subject and then telling it to the students, the traditional lecture approach, it has certain strengths and weaknesses. It actually works quite well for basic knowledge for the brain that's prepared to learn that. You know, that telling someone that's bad, you should avoid it, or that's good, you should look for them to eat them. Most of what the human brain evolved to learn falls in these categories as important for survival. And so it's relatively easy to teach this, it's relatively easy to test if it's successful and get immediate feedback on the results. But there's a problem if the learning isn't as simple as this. If the learning involves complex analysis or judgment or organizing large amounts of new information, or the ability to learn new information and apply it. This is, of course, what we mean by the kind of learning that we have in science and most university learning in general. And this is much more complex learning, and it's fundamentally different from this kind of learning. And one of the things that makes it so different is that it really involves significantly changing the brain. It's not just adding bits of knowledge to the same brain. You really, for this kind of complex learning, you're having to grow new neurons and produce proteins and so on that build and enhance all different sorts of connections in the brain. And so the net result is the brain ends up very different as a result of learning science, if it's successful. And so the question then is how to teach and measure this kind of complex learning that really is this brain development. And that brings me to really a different model for how to teach science. And it's one that I and a number of other people who are leading this effort are using. And so unlike what I said before, now you start with the goals, thinking what you really want students to be able to do, whether it's solve or design, analyze problems, or the capacity to learn. And then you go and create activities that have the students work with these activities, you give them feedback, that you try and target the creation of this desired expertise. And all the time you're doing this, you're looking at prior research, what it tells you about learning, what it tells you about learning these areas of science. Once you've designed these, then you use them, you have the students try them, and you measure the results. And if you're successful, great, you're done. If you're not successful, now what you do is you look carefully at why. And there's two possible reasons. It means that either your goals up here were unrealistic, or the treatment, the activities and feedback you gave didn't work right. And so you then modify whichever of these is necessary accordingly and try it again and do it again until you get successful results. Now, this is a very different way of thinking about teaching, but it's actually not a very different model because it's exactly the model for how we do science. When we do science, we have questions that we want to answer. We design and build the experiment to test those, to get that data. We run the experiment and look at the results. And if it comes out what we expect, that just confirms we understand that area of science. If it doesn't give what we expect, then you look at why. And it either means something was wrong with your goals, there was some important science you left out, you didn't understand, or it means, as most of my career was spent finding out, it means you built the wrong experiment, your experiment didn't work, and you have to fix it, improve it, until it actually goes through and works. So this is exactly the way we do science, and I'm simply applying this model to approaching education. And this approach has really given us many new insights on the traditional teaching of science and how to improve over what traditional teaching. And these advances have largely come over the past 1 to 2 decades, and we get research from these many different areas here that give a very consistent picture now about what's important for achieving learning. And this research comes from cognitive psychology studies about how people learn, different ways of thinking, classroom studies, mostly in the university science classrooms, and now, most recently, research about looking at the brain itself and how it functions. So what sorts of things has this research given us? Well, just to jump ahead, I'm going to give you the kinds of data that we get out from taking this new approach to teaching science. And so comparing here the model of just telling students which is the traditional lecture method, versus designing activities based on this scientific approach to teaching. And so if we look at just retention of information from lecture, that goes from something like 10% after, so only 10% of the information is retained, to nearly all of the information, more than 90% of it's retained 2 days later. In looking at mastery of basic concepts covered in a science course, that goes from 15 to 25% in the traditional lecture method, up to 50 to 70%, and this with long-term retention of this conceptual understanding. And finally, if you look about perceptions about science, what it is, how to learn it, these go with the traditional lecture method. Our data says that this becomes significantly less like a scientist. Use a scientific teaching approach, it gets much more like a scientist. So that's just data to show you we really can measure these things and see differences now. Finally, I want to say that these numbers, they improve using scientific teaching. They improve for both future scientists and non-scientists as well. The same methods help all parts of the student population. So let me talk about what goes into that and what has been learned from these studies. And I'm going to look at first what goes into identifying components of expertise and how expertise is developed, and then how to measure components of science expertise, and in particular what things the traditional exams that we give to students have been missing in determining what expertise they have. And then finally I'll finish with components of effective teaching and learning. Now, expert competence, research in expert competence is something that has been done extensively by cognitive psychologists. And they find that across a very wide range of different subjects, like historians, scientists, chess players, medical doctors, and so on, and many others, there are 3 basic components that make up expertise in all these different areas. The first is factual knowledge. Experts know a great deal of information and facts about their subject. That one is kind of obvious to people. But the others aren't so obvious. The second is experts have quite a unique mental organizational framework by which they organize all this knowledge and so that they can retrieve and apply it very effectively. And this kind of organization means that they recognize certain patterns or associations of information in consistent ways. This largely represents what we think about as scientific concepts. That's a way that scientists in an area organize large amounts of information in a consistent fashion. Now, the third thing that experts in all areas have is an ability to monitor their own thinking and learning. So they're able to ask themselves, do I understand this? Is this a sensible way to be solving this problem? And as they're doing that, they can bring in ways to check their understanding and monitor their thinking. Now, these 2 aspects here, these are really new ways of thinking. And what this research is showing is that if you just give people a lot of factual knowledge, they don't develop these ways of expert thinking. The only way these are developed is they require many thousands of hours of intense practice at actually doing this kind of thinking. And that's really what's necessary to make these changes in how the brain works that we now understand are necessary. So with this understanding of what it means to be an expert. A number of people in this area have now started to do research on different aspects of how well are students learning to think like experts as a result, or more like experts through their taking courses. And so let me start with what we know about measuring this conceptual mastery. Now, there's been a lot of studies of this, particularly in the areas of physics. And in the process of studying students' thinking, people have developed some very good tests of how well students are really able to understand and use these concepts. And the oldest and probably most widely used of these tests is something called the Force Concepts Inventory. And it tests the student's understanding of a set of basic concepts of force and motion that are covered in every first physics course, usually by having students have to apply these in some simple real-world situation, like a car running into a truck, or this is an example of one question from that test. It's a hoop sitting on a tabletop with a ball rolling around inside it, and asking, as the ball comes flying at the end of this hoop, which direction does it go? Now, the way this test is used is it's given at the beginning, at the end of when a student's taken a course covering this material. And so you measure what percentage did they not know at the beginning that they got right of these questions at the end. So that tells you just what percentage did they learn. Now, this test is being used in this way in hundreds of introductory physics courses now every year, primarily in North America, but there's a number of other countries around the world also using it. And the results from this are really very dramatic. If you look at the average student in one of these courses and you ask what percentage did they learn, on average, the students learn in a traditional lecture course, they always learn less than 30% of the concepts that they didn't already know at the beginning of the course. And this is just a compilation from 16 different courses of what this average value was. You can see that the highest is about 28%. And this holds true independent of the quality of the lecture, class size, institution. Some of this data is from Harvard University. Other data is from small two-year colleges. The amazing thing is it just doesn't matter. It says that this form of teaching is simply ineffective at developing an understanding of these concepts. And we now have similar data from other levels in physics and from other sciences that are telling us, giving much the same results. However, the good news is that we've also developed improved methods of teaching, which now, as measured by this test, consistently get up into this range. So far, far more effective than the traditional lecture method. Okay, let me switch to a different kind of expert thinking. This is really beliefs about certain aspects of the science. And if you interview lots of people, you find that their beliefs about science lie on a scale here that we go from novice to expert, like a practicing physicist here. And the kind of beliefs we're talking about here is, for example, the content of physics. To a physicist, it's this coherent structure of very broad concepts. To a novice, the content of physics is just isolated little pieces of information, and you learn that information just by memorizing all those pieces. The source of knowledge in physics, to a novice, it's just handed down by some authority, and physics knowledge in the classroom is completely disconnected from the world outside. Whereas to an expert, of course, these concepts describe nature and they're established by experiment. And then finally, physics problem solving. To an expert, it's using these systematic concept-based strategies that are widely applicable, including in new, completely new areas, which of course makes them useful. Whereas to a novice, problem solving is just matching the pattern of the problem you're giving with things you've memorized and just churning through without thinking. So once you understand that people's beliefs lie in this range here, you can set up tests that actually measure these for each student. And this is one thing my own group has been one of the leaders in. We developed this survey that allows to measure students' perceptions between where they lie between novice and expert in physics, and then we developed another exam that did the same in chemistry, and there's just about to be published one in biology as well. And so the way these exams look is they have typically 40 statements in which the student says how much they agree or disagree with the statement. And so 2 from the physics exam is, for example, understanding physics basically means being able to recall something you've read or been shown, or I do not expect physics equations to help my understanding of the ideas, they're just for doing calculations. So the student then marks how strongly they agree or disagree with each of these statements. And each of these statements, by the way, we know that all practicing scientists in this area give it one very consistent response. We've tested that. So the way this exam is used is like the previous one. You give it before the students have taken the course, and then you give it after they've successfully completed the course, passed the exams, and so on. And you want to see how did their perceptions of science shift as a result of having the course. Well, what we see, and the others who are studying this, is that essentially all introductory physics courses leave the students more novice-like in their perceptions of science after they took a physics course than they were before they ever had the course. So it's actually, in this measure, the students are actually not only not learning, they're being worse off than they were than before they ever had courses. We more recently started getting data in chemistry. It looks just as bad or worse than physics, and biology is also just about as bad. So, okay, so that's the bad news. Let me now turn to the good news things of what we know about effective teaching and learning. And so I'm going to start with certain basic components of effective teaching and learning that apply really to all levels of learning and almost all settings as well. First is the importance of motivation, the need to connect and build on the prior thinking of the learners, the reducing unnecessary demands on working memory, and I'll explain what I mean by that. And then finally, the explicit practice of expert thinking in an extended and strenuous way. And emphasize the extended and strenuous practice here, because what brain research has shown in the last 10 years or so is that the brain develops quite differently than people used to think. Now we realize it's much more like muscle development. So if I want to build up a muscle, everyone knows I have to exert it as, very strenuously, and I have to do that over and over again, and that muscle gets stronger as a result. We now know that the brain acts much the same way. You have to make it really work very hard, and you have to do that over and over again, and it develops in response to that. Okay, so I'm going to go quickly through and discuss what research tells us about these different elements here. Motivation, there's lots of research on it. I'm just going to give basic ideas. The first is it's very essential. If someone doesn't want to learn something, they won't learn it. But we do know a few important things for motivating learners. The first is making the subject relevant and useful and interesting to the learner. Second is giving the learner a belief that they can master the subject. And third is giving a person some level of personal control or choice in the learning process. All of these things motivate people to learn much better. Second, connection with and building on prior thinking. That's just the idea that you're developing the brain, and so you have to understand where the brain is and how it starts of the person you want to be learning. And this prior thinking affects then all of these other aspects of what's important in them. So I'm not going to talk more about that. I'm going to go right to this working memory issue. If you study memory, a sort of simple view of the way memory works is there's the long-term memory. That's what we mostly think about as memory. It has this enormous capacity. You can remember things for long duration, but it's hard to get things into this long-term memory where it stays. And to get into it, it basically has to come through this short-term working memory, it's called. It's very easy to get things into. It's what you use if you're learning things in a kind of hour time scale, like from this talk. It's easy to get information into it, but it's quickly lost and forgotten from there. And this short-term memory has a very limited, very small capacity. And so this is something that's extremely easy to test and very well established from cognitive science. And it's nicely represented by this cartoon that the student's brain any person's brain just very quickly fills up if you give them too much information. Now, in fact, the precise number is that the typical human brain can remember and process a maximum of about 7 distinct new items at once. And the way it functions is very much like a PC with a small amount of RAM. And so the more things you give it to do, the less effectively it works. And in fact, of course, 7 distinct new items, that's a tiny amount compared to what's presented in the typical science lecture when you realize that one new technical term, for example, is 1/7 of the capacity of the working memory. And so, because of this, what you would predict is that the amount of a person who doesn't know a subject they could process and remember from it would be a tiny fraction of what was actually presented. And this is exactly what the research shows. And just one example of this is what a study Kathy Perkins and I did in introductory physics courses, where we took some non-obvious but important fact that was presented in the lecture, and then we just tested students if they remembered it 15 minutes later, and we found that only about 10% of them actually did. So anything you can do to reduce this unnecessary demands on working memory will actually improve learning. And so you can think of it as very much the mental equivalent of if you give a student one package to carry, they can cover a lot of progress rapidly, If you load them up with several things at once, then they struggle much more and they can't make as much progress. And if you do the mental equivalent of dropping a very large number of packages on them all at once, you just effectively, mentally squash them flat, and they can't really process and learn anything from that experience. And so the way you need to, in teaching, anything that reduces this extra use of working memory will improve. So reducing the use of technical jargon to an absolute minimum, using figures as much as possible rather than relying on the student to have to listen to a bunch of explanation and then create in their own mind an image for what you're describing. Use of analogies, of having things that the student's familiar with that represent similar relationships. That greatly helps reduce the working memory because they can use their long-term memory as an aid. I will point out one very common teaching mistake that actually increases the demand on working memory. And this is a mistake that many people who are experts in a subject think would be the best way to teach something. That's that you'd present all the pieces of background knowledge and math procedures, and for example in physics, first, and then you would give the student some problem to solve and uses all these pieces and put them together to solve the problem. The problem with this is that this approach makes sense only if you already know the subject. If you don't know the subject, if you're the student, then all of these pieces here are just completely disconnected facts that you can only learn by memorizing them as separate things. This means it takes up lots of working memory as well as being rather boring to learn. And so actually a more effective approach is to start out by first presenting a problem to the students that's interesting. And then you bring in the facts and procedures as the steps to solve this problem. This builds their expert connections and mental framework for all of this information. That means that it reduces the working memory because they don't have to think about these as all separate things. They're connected facts, and it's just one single item rather than many separate ones. Plus the fact it's much more motivating to learn because they see these are solving, there's a reason for them to learn. Okay, finally I'm going to move to the last item, which is how to give this authentic practice of expert thinking that you need to do over an extended, strenuous period of time. And so the first thing is you need to exercise the brain. So you need to give challenging but doable tasks or questions to the student. And these questions need to really think about what makes up expert-like thinking and involve the student have to use these. So thinking about concepts and developing models in their mind about how these work. And then recognizing what information is relevant or irrelevant for solving the problem. And checking if things make sense and why. And because these are all very much these kind of expert-like ways of thinking that develop only with practice. And so while you're doing this, then the teacher is very important for providing effective feedback to guide their thinking. And that means it needs to be very timely, right as they're thinking, and quite specific to guide them. And so in much the same way an athletic coach watches the students, the players on the team do things and immediately tells them what's the things that are good or bad, you need here the teacher to act as a cognitive coach to give it guidance to the students' thinking right as they're doing it. Okay, so that's in the abstract. How do you actually do this in class? In particular, I've been worrying about how to do it in large classes with hundreds of students, and how to use research and practices that work and use technology to help. And I think particularly with this large number of students, you have to use technology. One of the obvious ones is books. I'll talk about that in a minute, but other things are other kinds of technology I can explain. So now I'm going to give you an example of an actual lesson from my class in teaching basic electricity. So the students start with an assignment. Before class, they have to read the chapter on electric current, and from that, they have to learn all the basic facts and terminology. And then class starts out with just a short quiz to check that they've done that and reward the ones who did. That's motivation. But then the class, rather than me spending any time giving them information, they already got that from the reading. Then it's based around a series of questions. And so we would start with the question here that with this switches, this light bulb here will, and the students have to decide whether it's going to stay the same brightness, get brighter, get dimmer, or go out. Now, every student in the class has something called a clicker, and this is a device. It's like a very simple TV remote. It's about the size of this laser pointer with 5 buttons on it, and costs about $30. And the student picks which answer they think is right and presses the corresponding button here. And that signal is picked up by a computer that then records who the student was and which answer they chose. Normally, before I would tell the students what the right answer was, so they first have to answer individually, and that gets them really primed to think about it more. Then they would discuss in small groups. So throughout the large lecture hall, each small group there'd be students would break up into small groups, and for a minute or two they would discuss which was the right answer here and the arguments for them, and then they re-vote. And while they're doing that discussion, I'm going and listening in on them so I can get a better idea of what things they're confused about, what aspects they understand. And then we can show them, we can get them to give their reasoning, and we can show them then the response from the histogram of what all the students in the class, which answers they chose. Now, many times when we just then talk about the subject, talk about the question, but in this particular one I would use some more technology, which is a simulation. And so this is actually an interactive simulation from a project I run that's developed a lot of these, and you can, the instructor or the students can build any circuit they want. So I can try this out. So I would show this to the students, and then we would do the experiment of connecting it. They would see what happened. And so we would, in the class, I show them the simulation, and then there's a follow-up discussion of where I would review the correct and incorrect thinking. It turns out it's at least as important to talk about what answers are wrong and why for helpful guidance to the students as it is to talk about what's right. And then you go on to extend those ideas. You can, in a class like this, and particularly using those simulations, that generates many more questions from students where they're making predictions, asking about further things. That's really extending them, moving through the material you want to cover. So that's basically how the lesson would move. Now, I'll just review how this is practicing this expert-like thinking that I'm talking you want to do. You see, first, it starts out with a challenging but doable question. This is the question that I posed about the light bulbs. Now, this question is not chosen accidentally. It's designed because we know there's certain basic difficulties students have in really picturing what's happening with the flow of electricity. And asking this question gets them to focus very explicitly on their mental models and identifying what's right and wrong about it to help them with what's fundamentally, for beginning students, quite a difficult concept. Then you can see that the many aspects of the explicit focus and expert-like thinking. They have to work very actively developing their concepts of electricity and their mental models of how the electrons flow. They have to look at that and think about what's relevant and what's irrelevant information. Again, this is something that is very much an expert skill that you get with practice. And then they're checking, they're seeing things, if it makes sense. They're reflecting on their understanding through seeing what answers are right, testing themselves, and most importantly, in their discussions with their fellow students. And finally, they're getting this critically important, timely and specific feedback, and they're getting it in many different forms, both from the discussions with fellow students and the feedback they get in that. They're getting by seeing the histogram of results from the different students in the class and testing themselves and getting the right answer. And then finally, they're getting it from the instructor, who at the end is discussing what's right and what's wrong. And because I, as the instructor, know much more about what their thinking is through the use of this technology, I can be much more useful in how I explain things. And then finally, they're very engaged in this. They're busy having to think all the time. They're exercising their brains, which is what I keep saying is absolutely the essential aspect of developing this complex learning. Now, this isn't a good start, but there isn't enough time in any class to really move students very far along in developing this skills and expertise. There's just not enough time for the brain to change. It takes these many, many hundreds to thousands of hours. And so for true learning, what has to happen is there's got to be further practice of the students. And that really means extensive, well-designed homework that require the same kind of expert thinking and allow feedback to the students. And this has to be done repeatedly, over and over again. That's really what gets things into long-term memory. It's what establishes long-term retention of learning, this repeated practice spaced out over time. And so it's when you do these kinds of things, you put this into class, that you get this kind of data that I showed about before, with these dramatic improvements in learning compared to the traditional lecture method. So just to end here, in summary, I presented this scientific model for thinking about science education, and as I said, I think we can make good arguments. These apply to education in many different areas, not just science. It's clear we can achieve much more effective education, and it's more fun, both for the students and for the teachers involved in this. And so finally, if you want to learn more about this, here are some references ranging from a book from the National Academy of Sciences in the US on how people learn. This is a long, well-written book, and then they get shorter and more poorly written down to this short article I've written here that's available at this website. And then some of the specific research I mentioned, the research, this survey on beliefs and perceptions about science, and the research we've done looking at that is available at this website. And then these simulations, and we now have about 80 of these for teaching all different areas of science. Those are available at this website, and you just download them for free if you want. And then we have many more resources available to that website there. So I think I'll just leave this up for now, so if people want to make notes of these references, I guess they're in your books anyway. So I think now there's time for some questions. Is that okay?